Hello, my name is Fabian Panse, and welcome to our talk about generating test datasets for duplicate detection at scale using historical voter data. The first question you may ask is, why do we need such test datasets? To understand the answer, you need to know that duplicates are data records that refer to the same real-world entity. The detection of such records is an important task in many data management processes, including data cleaning, data integration, and data linkage. In research, we need to evaluate duplicate detection results if we want to analyze the quality and behavior of newly developed algorithms, but we also need to evaluate them if we want to find a suitable setting of algorithms and their parameters in a particular use case. Existing datasets, however, are either very small because they have been manually labeled, or contain artificial errors and unrealistic outdated values. So we still have a need for large test datasets with real data errors. The goal of our study was to extract a test dataset with labeled duplicates from historical voter data. Here we have defined several requirements. First, the resulting dataset should have a high quality. This means that the duplicate labels, aka the gold standard, are correct. It does not contain many exact duplicates, and it contains many real-life errors of various forms so that we can test algorithms under real but also difficult conditions. The second property concerns the dataset's usability, which means that we can use it to customize smaller datasets based on the needs of the individual users. This requires that we have many and large duplicate clusters to choose from and duplicate records of different degrees of similarity. Such a customization can be supported by storing pre-calculated similarity scores within the test dataset. Finally, we plan to extend our dataset with future updates of the voter register. However, to enable a fair comparison of evaluation results made by different parties, it is important that we provide mechanisms that allow the user to reconstruct earlier versions of the dataset. As input to our study, we choose the voter register from North Carolina, which is considered public information per NC General Statutes. This register publishes a new snapshot at every election and the end of every year. Today, it includes more than 40 snapshots and covers a time window of more than 15 years. With the NCID, it provides a statewide identifier that is valid across individual snapshots. The voter data are often recollected at each election using hand-filled forms, resulting in a lot of data errors and variance between duplicate records. Finally, the register regularly changes some parts of its own vocabularies, which introduces additional differences in the duplicate records. In summary, the statewide ID allows us to connect the individual records based on their corresponding real-world entities, and thus to construct a sound gold standard. The hand-filled forms and the changing vocabularies ensure that we have many real and diverse errors. The large time span provides us many outdated values, and the large amount of snapshots yields us many and large duplicate clusters, which made this register a perfect source for our study. Now let's take a quick look at the generation process. First, we scanned over the different snapshots, converted them into UTF-8, and then scanned over the individual rows. For each row, we loaded the corresponding duplicate cluster from the already existing part of our test dataset and used the MD5 algorithm to check whether the new row is an exact duplicate of one of the already existing records or not. If not, it was inserted as a new record. If so, the statistics of the dataset were updated. We then repeated this process for every row and every snapshot. Finally, we calculated different kinds of similarities between the duplicate records and stored them in the dataset as well. To store the dataset, we choose MongoDB because it is scalable, aggregation-oriented, and supports the storage of sparse data. The resulting dataset contains 120 million records, forming more than 30 million duplicate clusters and around 650 million duplicate pairs. Its largest cluster has 77 records, and its average cluster size is almost 9. An essential part of our study was the pre-calculation of similarity scores. Here we distinguish between two kinds of similarities. The first one is a plausibility. It should measure to what extent the given duplicate labels are sound, because we found some records that have the same NCID but probably do not refer to the same person. Nevertheless, we have the basic assumption that the given labels are correct, and we have only looked for clear contradictions to this assumption. For this reason, we use only attributes that are either very identifying or very discriminating and that rarely change. Moreover, we use the similarity measure that compensates small differences, such as typos or swap tokens. It is important to note that we incorporated external domain knowledge into this calculation process. On the right side, we see the results of our measurements. 92% of all duplicate pairs have a plausibility of 1 and are not presented in this figure. Most of the remaining pairs have a high plausibility as well, and only a few pairs have a plausibility lower than 0.5. At the top of the right side, you can see excerpts of 2 sample clusters. In the case of the first cluster, we have typos and values confused between different attributes. Nevertheless, these differences are likely data errors and no clear indication of non-duplicates. In contrast, in the second example, we have clear contradictions, such as the different names, the distinct gender, and the large difference in the age values. Here you can see the corresponding plausibility scores of the 2 clusters, and as we expected, is the score of the second cluster much lower than this of the first. The second similarity that we computed represents a kind of dirtiness and should be used to quantify the difficulty of detecting duplicates within the dataset. Here we used every attribute and used a measure that reflects any kind of difference between the duplicate records. However, some attributes have a larger impact on the difficulty than others, therefore we weighted them by their uniqueness. Finally, when we want to evaluate algorithms on datasets with different degrees of dirtiness, we should be able to compare these scores. Therefore, we decided that we did not include any external knowledge into the measuring process. As you can see on the right side, although we have eliminated all exact duplicates, many of the remaining duplicate pairs are very homogeneous. Nevertheless, even if very small in percentage terms, we also have a large number of pairs in higher ranges of heterogeneity. What we see even more clearly if we compare these scores with those of the 3 popular test datasets Cora, Census, and CDDB. As an illustration, our 2 sample clusters have both a heterogeneity between 0.35 and 0.4. Here it is to note that the second cluster actually consists of 10 records, where half of them are similar to the first and the other half are similar to the second record. Finally, we made an experiment to show how the pre-calculated heterogeneity scores can be used to customize datasets of different degrees of dirtiness. Here we executed a very simple generation approach. First, we selected 100,000 clusters. Then we iterated over the sorted list of records in each cluster and removed a record if its heterogeneity to one of its predecessors was not in the requested range, which was expressed by the 2 thresholds h-bottom and h-top. This is illustrated at the left side for a cluster with 9 records defined within a 2-dimensional space. In this example, the cluster is reduced to 3 records. Finally, we sorted the reduced clusters by their size and selected the 10,000 largest clusters as the final test dataset. Below, you can see 3 datasets that we created with this approach by using different settings of h-bottom and h-top. All 3 datasets have similar numbers of records and duplicate pairs, but their heterogeneity scores differ significantly. Now, here you can see the results in form of F1 scores of different duplicate detection algorithms that we applied to the 3 datasets. And as expected, the dirtier the dataset, the harder it was to detect the duplicates, which shows us the value of using the pre-calculated similarity scores to customize datasets of different degrees of dirtiness. As a comparison, we applied the same algorithms to the Cora, Census, and CDDB datasets, and the results are similar to the ones of NC2. In summary, we were able to generate a test dataset of large size, and although many of its duplicate pairs are very similar, it can be used to customize datasets of different degrees of dirtiness. In future work, we want to generalize this approach so it can be applied to other historical datasets as well. The problem is here that many datasets will not have as many data errors as a voter register. Therefore, we also plan to combine it with an existing test data generator that is able to inject artificial errors at will, and so to combine the strength of both approaches, having real outdated values on one hand and having a flexible error injection process on the other hand. Finally, we applied a simple algorithm to customize test datasets by simply using 2 thresholds. Here we are looking for more sophisticated methods. So this is the end of our talk. Thank you very much for your attendance, and we are open for questions.